Hi, grade 12 physics students. Today we're going to look at some rocket science. I hope you're ready. So what that means is we're actually going to look at the topics of general gravitational potential energy. So we're going to look at escape energy, how much energy you need to actually escape from a planet, and we're going to look at escape velocity as well. And so I hope you've had a chance to watch the video that I posted as well. That's a YouTube link that just explains some of this problem with getting outside of the gravitational energy well of a planet. So this is just a pre-made note that I'm going to walk you through, and we're going to hopefully highlight any questions you might have through the note as I go. The first thing we need to note is that gravitational potential energy exists between masses because of the force of gravity. We know the force of gravity between any two masses is g, which is the universal gravitational constant, times the first mass times the second mass. So if it's you standing on a planet, you're one of the masses, the planet's the other mass, divided by the radius squared, the distance between the centers squared. So don't forget that this is actually the distance between the centers of mass. Not necessarily the height you are above a planet. If we consider two masses, let's consider one that's much more massive than another. So capital M for the bigger one and small m for the smaller mass. Maybe you and the Earth, or a spaceship and the Earth, something like that. They start with a separation of r1, and they move apart to a separation distance of r2. If r2 is bigger than r1, what happens to the gravitational potential energy of the system? Well, intuitively, we would say if R2 is bigger, it has to be that the gravitational potential energy is increased. But the question we're after really is by how much. Now remember that the force of gravity universally is gm1 m2 over r squared, which means that the force of gravity is proportional to 1 over r squared. And so when we plot the force versus the radius, and we plot a proportionality of 1 over r squared, we find this curve that actually plays out as shown. Now we know, looking at that curve, that is not a linear relationship. So we know that we can clearly, when we take the average between the force of gravity that I start with right here and the force of gravity that I end at right there, Fg2, that we can't just add those together and divide by 2. That would be an arithmetic mean. If you've taken data management before, any type of statistics, you know that that we would call this, in this case, a geometric mean. And that's because, if you think about it, if you've done this in grade 11 math, you've done geometric series, and we know that that's a curve that looks very similar to that. And so this is a geometric mean. So instead of adding the forces together and dividing by 2, the geometric mean is the square root of the first force times the second force. There's a little note here on the side that says, on a force versus distance graph, energy is the area under the graph. Well, let's just highlight that again down below. You can see down below on the left side, I just noted that the area is the gravitational potential energy, since the area is the force of gravity on the y-axis times the change in distance between centers on the x-axis, and we know that force times distance is the work done, which is an energy. So therefore, that has to be the gravitational potential energy. Well, with that in mind, how do we actually find that area? Well, we know that average force multiplied by the change in the distance between centers must be that area. And so if we know, because it's a geometric mean, that the average force is the square root of Fg1 times Fg2, and the change in R is R2 minus R1, then we can simply multiply those two things together. So because of the equation for the force of gravity, we see that Fg1 becomes this, and Fg2 becomes this, noticing that one has this, the only difference there is that R1 squared and R2 squared. And so because of that, we have g times itself, capital M times itself, small m times itself, so we can square that in the next line there. And then we can multiply R1 squared times R2 squared in the denominator on the next line. So if I keep moving forward with that question, what we see is that the square root of everything that's squared means we can get rid of the square root and get rid of the squareds, because it just gives us back the original value. And so we have GMM over R1, R2 times R2 minus R1. Now what I'm going to do is I'm going to expand this out. So I'm literally going to take the whole number here. It is a number. We could put a bunch of values in to get a single number there. And we're going to multiply by each of these. And so that would give me R2 times the first times that GMM over R1, R2, and then minus R1 times GMM over R1, R2. Notice here that because you have R1 in the top and bottom and R2 in the top and bottom, that those will cancel out, which simplifies our life a little bit. That gives us the change in gravitational potential energy, and you notice I've noted there it's not just gravitational potential energy, it's the change in gravitational potential energy. Why? Because two things are being subtracted. It's a later one minus a previous one. In fact, right now it's previous minus the later, and so we're going to see how to rearrange that in a second. But if we have a difference, a subtraction, that means it's a change in that value. So the change in gravitational potential energy is equal to GMM over R1 minus GMM over R2. But we know right here that the change in gravitational potential energy, based on every definition that we've used so far, is the second minus the previous. So how do we get that? It better have the first term better be R2 and the next term better be R1. And so in order to do that, we can just switch the order, right? I'm going to take this whole term here, I'm going to move it to the beginning. And then in order to write it as, so what that would be is that would be a plus sign here. But then in order to write it as a difference minus that value, we're going to write minus a negative value. And so in general, gravitational potential energy at any point is negative GMM over R. Notice it's not an R squared. R squared is the force, R is the gravitational potential energy. The change in gravitational potential energy, what we're going to be interested in, for example, putting satellites into orbit and things like that, is incorporating things like that. Gravitational potential energy itself will be how much energy it takes to get completely free of that object's pull. All right. Moving on here, we can see that there's some differences then between the force of gravity and the change in gravitational potential energy. First off, as I already noted, the gravitational potential energy is 1 over R, not 1 over R squared. We also note that EG is negative, and the reference point for this is an infinite distance from the planet. In other words, if you are an infinite distance away, if the distance you are away is infinity or approaching infinity, only then is the gravitational potential energy going to be equal to 0. Then and only then. You're never going to get there. It's really a limit. And those of you who've looked at limits know that you're approaching it but never reaching it, and that's really what's happening here. So you might want to just note that. Now notice here as well it says but, I should change the by to a but there, delta EG can be positive. And let's see a case of where it would be. If we start at EG1 at some distance R1, and we move to EG2 at some distance R2, you can see there that subtracting EG2 minus EG1 would give us a positive change in gravitational potential energy. There's a little note here at the side that says this: EG is always negative, which means as a mass gets further away from another, that mass's gravitational potential energy increases by becoming less negative. All right, so the further away you are from a planet, you get less negative in your gravitational potential energy. You never get positive. The change is positive, but not the actual gravitational potential energy that you have at that moment. All right, so let's look at a couple special cases. The first one I want to look at is when the gravitational potential energy approaches negative infinity. When two masses are very close together, they have a very large negative gravitational potential energy. For example, you being on the Earth have a very large negative gravitational potential energy. Well, why? Well, if you look at the equation, we know gravitational potential energy is negative GMM over R. And if R is approaching 0 or very small, just think of it like 0.000001, but these other values on the top are very large, what you get is you get this limit where it approaches negative infinity. And so that's the occurrence only when two objects are very close together. A second case where a limit plays in is when the gravitational potential energy approaches 0. Well, that happens when the radius approaches infinity. Or there's a second case that could happen in, and that's when the other mass is 0. But you know or I know of any mass that is truly 0. So the only case that can happen then is when the radius is approaching infinity. Other masses need to be so far away that there's no force of gravity to bring them together. Now, if you had only two masses in the entire universe, there would always be a force of gravity between them. And so regardless of how far apart they are, so that's why we say it has to be an infinite distance apart. Well, what is infinity? Well, you got to keep going. Oh, I've reached infinity. No, you haven't. Keep going. So this is a limit. It's not truly a number that we can truly capture, but we can be as close to that as possible, assuming that if we get to a very large number, we've basically escaped the gravitational influence of the other object. What we call this is a potential energy well. In order to escape from a gravitational potential energy well, we have to give an object more energy. Well, how much energy do we need to give it? We need to give it the energy required to escape, called the escape energy. What is the escape energy? As I just noted, it's enough energy to get the total energy to be bigger than or equal to 0. If you can get it to be at least 0, then you've escaped the pull of the other planet or the other object, and you're free of it. And so that's the limit, right when it is 0. But it can be any energy that makes us above 0 as well. We know that kinetic energy is always positive. We know that gravitational potential energy is negative, as we've just derived in this lesson. And so if the total energy needs to be bigger than or equal to 0, then the two types of energies that we're going to use here, we're going to ignore air resistance as we escape the planet Earth and things like that. But that does come into play in reality. But we're using the ideal case where we just have gravitational potential energy that needs to be overcome by kinetic energy. Kinetic energy is 1/2 mv squared. Gravitational potential energy is negative gmm over r. And so that's what we get by putting those together. I'm going to rearrange this by bringing gmm over r to the other side, add it to both sides. I notice that the masses that I have here, assuming this is like a spaceship and Earth, the mass of the spaceship is on both sides there. We can cancel it out. And rearranging this for v squared, I'm going to multiply both sides by 2. If I multiply both sides by 2, that gets me 2gm over r. And then I take the square root. And that square root suggests that any velocity that is equal to this or bigger than this is going to be high enough to allow me to completely escape from the gravitational pull of Earth, which is quite remarkable that we can actually find this. And what's more remarkable is that we can actually get close to actually reaching these speeds. To just have enough velocity to escape Earth's pull, we need to have this escape velocity. I've taken that and just written it as an equal sign because it's just enough energy that we need. If we actually put some numbers in here, we know that the mass of Earth is 5.98 times 10 to the 24 kilograms rather, sorry. And we know that the other values are listed there as well. What we get is we get 1.12 times 10 to the 4 meters per second. That is 11,200 meters per second, or if you were driving in a car or flying in an airplane, 40,320 kilometers an hour. Most airplanes most commercial jets get up to about 1,000 kilometers an hour at their max possible speed. So we're talking 40 to even 50 times a jet plane is the speed we need to completely get out of Earth's gravitational pull. That is fast.